This presentation is on probability. So we're going to start with relative frequency. The probability of event A, or the relative frequency, is the number of times event A occurs over the total possible trials. For example, if there are 6 sides on a fair die with sides having numbers 1, 2, 3, 4, 5, and 6, and an equal chance for each outcome to occur, then the probability of rolling a 4, for example, is 1/6. Note the notation. P parentheses 4, the probability that a 4 will result is 1/6. We say that dice are loaded when the probability of landing on each side is unequal. Another concept is the complement. The complement of event A is 1 minus the probability of A. So for example, let's say we want to find the probability that it'll rain tomorrow, and we know it's 10%. Then the probability that it won't rain tomorrow is 90%. We know that intuitively, but actually we get this from the rule. The probability that it'll rain tomorrow is 1 minus the probability that it won't rain tomorrow. We often use the symbol A with a bar over top of it to denote the complement of A. Note that the complement of A is 1 minus the probability of A. So if the probability to roll a 4 on a die is 1/6, the probability that you do not roll a 4 on a single fair die is 5/6. Note that all probabilities in an experiment must be within the interval from 0 to 1 inclusive. For example, what is the probability it will snow in Southern California in June? 0. And what's the probability that there will be oxygen in the air tomorrow? That's 1. What we know is that no probability will be greater than 1 and no probability is negative. Plus, the sum of all probabilities in an experiment must add to 1. That is why the probability that it will rain tomorrow is 10% and the probability it will not rain tomorrow is 90%. Both add to 1. Probabilities are often given in distributions, so that comparisons can be made, and we can use this probability data to help us be more prepared and make better decisions in our organizations and personal planning. For example, according to the Red Cross, the probability of blood types in the United States are as follows. Where are you in this probability distribution? Now let's talk about compound events. Compound events are when 2 or more events occur. In computing the probability of compound events, we must consider whether one event is dependent upon the other or if the events have common outcomes. If we consider the probability distribution of blood types, we want to compute the probability that a Hispanic member of the population has either O positive or A positive blood types. We can add 53% to 29% and we get 82%. That means that there's a high probability, 82%, that a given Hispanic member of the population has either O positive or A positive. The probability that they do not have one of these 2 blood types, and rather they have one of the other 6 blood types, is 18% using the complement rule. Let's see why this is true and the mathematics behind this. For example, if we have a standard deck of cards, we have 52 cards in the deck. They're divided into 4 suits: hearts, diamonds, clubs, and spades. So 52 cards divided by 4 is 13. There are 13 cards in each suit. Suits have ace, king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, and 2. Thus, for example, there are 13 hearts in a deck and 4 aces in a deck. The probability of pulling an ace out of the deck is 4 out of 52, or 1 out of 13. The probability of drawing a heart from the deck is 13 out of 52, or 1/4. However, sometimes we want to find the probability of A and B. If the 2 events are independent, then the probability of A and B is equal to the probability of A times the probability of B. Now let's consider a compound event. We want to know the probability of drawing an ace or a king. The first thing we have to ask ourselves is there an overlap between aces and kings? We can see this in the following Venn diagram. These 2 events are called disjoint. Notice that there are no aces that are kings or kings that are aces. We say these 2 events are mutually exclusive. 2 events are mutually exclusive if they have no common outcomes. The formula we use in this case to find the probability of a compound event is the probability of A or B equals the probability of A plus the probability of B. In this example with aces and kings, the probability of an ace or a king equals the probability of an ace, which is 4 out of 52, plus the probability of king, which is 4 out of 52. This gives you a probability of 2 out of 13, or 0.154. Generally, we round to 3 decimal places unless the probability is 1/4, 1/2, 1/3, or other basic fraction. Now, if the 2 events are not mutually exclusive, then the formula is slightly different. For example, let's say you want to find the probability of an ace or a heart. Notice this time in the Venn diagram that there's an overlap. The common element is the ace of hearts, and we cannot count this twice. So to compute the probability, we add the probability of drawing an ace plus the probability of drawing a heart minus the probability of drawing the ace of hearts, so we counted twice. We call these OR rules, which suggests addition. We are adding the probabilities to get the result. Remember though, when we add, we can only count each probability once. However, sometimes we want the probability of A and B. If two events are independent, then the probability of the outcome is the probability of A times the probability of B. So what do we mean by independent? Two events are independent if one event has no effect on the other. So we ask ourselves, does one have a bearing on the other? For example, if we have two smoke alarms powered by our home electrical system, are these events independent? In other words, if one smoke alarm goes out, can we count on the other? It sure sounds like the two are independent smoke alarms. However, if the power goes off, then the two outcomes are definitely dependent. Let's try another example. If the probability of tossing a coin is 1/2, then the probability of tossing a coin twice is independent. Why is this true? Did getting a head on the first try impact getting a head or a tail on the second try? No. These two events are independent. So the probability of A and B equals the probability of A times the probability of B. Now let's look at a contingency table of helmet use and head injuries. According to the Journal of the American Medical Association, we have this data: head injuries, not injured, wore a helmet, and no helmet. We add the rows and columns first. The probability of getting a head injury equals the number of head injuries divided by the total, or 576 divided by 3,562. That equals 0.162. The probability of getting a head injury, given that the person wore a helmet, is slightly different because we are now looking at only those who wore a helmet. This probability looks like this, and we get 0.128. Or let's say we want the probability that a person has a head injury given that they did not wear a helmet. This time we're dividing by 2,810, and we get a result that's 0.171. We can see from these results that the probability of getting a head injury, given that you're not wearing a helmet, is higher. The question is it significantly higher? We will answer that question in a future episode when we're talking about hypothesis testing.